Hello everyone, my name is Odinaka, and I'll be going over hardware-based neuromorphic architectures beyond crossbar arrays with a main focus in reservoir computing. So at its core, neuromorphic computing is an approach to artificial intelligence that seeks to mimic the architecture and function of the human brain. So this means designing AI systems capable of learning and adapting in a more similar way to human cognition compared to that of traditional AI algorithms. Hence, the basic building block for a neuromorphic computing system is artificial neuron. And similar to how biological neurons work, artificial neurons are designed to receive input signals from other neurons, process the information, and then transmit output signals to these other neurons. So by connecting these large numbers of artificial neurons, these neuromorphic computing systems can simulate the complex patterns of activities that occur in the human brain. So some key differences between the traditional computing and neuromorphic computing, I outlined for them here. And the key thing here is with the processing and adaptability that neuromorphic computing has compared to that of traditional computing. So in the case of traditional computers, they process information separately for both data processing and data storage. But with neuromorphic computing, they are able to use distributed network of neurons to process information in parallel. And this parallel processing is really key because it allows for information to be processed more quickly and efficiently, and is more resilient in errors and noise because we have the system that is working together versus the traditional where the system is working separately. And another key feature here is the fact that with neuromorphic computing, they're able to do real-time adaptation. So similar to how the brain works, for instance, if you're trying to recognize a human face, you look at multiple faces, and then from there, your neurons are able to easily determine how a face does work. So that's how a similar principle that neuromorphic computing uses. So as I mentioned before, the basic building block of neuromorphic computing is the artificial neurons, and researchers have been able to go beyond software simulations to creating hardware-based systems that do emulate how a neuromorphic system is meant to work. So during this presentation, I'll go over two of them, but for the sake of time, I'll probably focus more on the reservoir computing. Now, reservoir computing has two different parts to it. So the first part is the reservoir part that performs complex nonlinear transformation of input data into a high dimensional output data. So over here, dimension just represents the number of linearly independent outputs. And in this process, the reservoir would temporarily store the information of past inputs to make the output depend on both the present and past inputs. So this is what they call short-term memory effects. And the second part of the reservoir computing is to conduct a linear transformation of the outputs from the first part. Now, in this second part, it requires you to train, to have a trained data set that will help optimize the parameters of the linear transformation so that the final output is much more accurate and desirable. But with the first part, the reservoir part, it doesn't require any training as it performs its own transformation with fixed parameters. So what this means is that with the first part, that has the that creates the essence of how the reservoir computing works and makes the reservoir computing a very suitable aspect or model to use for neuromorphic hard-based implementations. And the reason is because the learning process is independent or doesn't interfere with how the reservoir dynamics are created. And because of that, we can use any material that provides the appropriate complex dynamics and memories that we do need. So the next question is how we can implement a physical system using complex nonlinearity as well as memory effects with short-term properties. So there, okay, yeah. So here, Okay. So yes, so there are different ways that people have tried to create the reservoir needed in reservoir computing. And they've tried using photonics, crossbars and thistles or lacks of that. But they found out that using non-magnetic systems is much appropriate or suited to act as a reservoir for several reasons. So one of the key properties of nanomagnetic systems is the fact that they have a magnetic hysteresis loop, which provides a nonlinear response that we do need for our reservoir, and by stable remnant magnetization that acts as the basis for the system's memory, which are two key features that we need for neuromorphic computing using a reservoir. The second thing is that it exploits the magnetic and electrical properties of electrons to help increase energy efficiency, as well as decrease the area requirements. And using different magnetic textures, we're able to also create a system that emulates the functions of a neuron, which is the basis of using neuromorphic computing. Now, there are several devices out there that we can use as a nanomagnetic reservoir. But for the remainder of this presentation, I'll mainly focus on the spin torque oscillator and some of the work or experimental results that researchers have already achieved using this device. Okay, so the way, so for the remainder of the slides, I'll call spin torque nano oscillators as STNOs. And STNOs are a type of magnetic tunnel junction, which can serve as synapses and neurons, which are the main basic blocks of the neural network of the brain. Now, MTJs are of particular interest in neuromorphic computing systems because they're compatible with standard integrated circuits, as well as can support multiple functionalities such as high scalability, high speed voltage operation, as well as non-volatile memory. So with the way STNOs work, they work by passing a DC current through the multi-layer structure. So looking at the image on your right, we have a multi-layer structure represented with the ferromagnetic layers represented in gray and the insulated layer represented by blue. So what happens there is that we have DC current being passed through one of the layers, which we call the free layer, and that causes the magnetization in that layer to oscillate due to some spin torque effects, and the frequencies that are produced range from hundreds of megahertz up to tens of gigahertz. So when the magnetization of this free layer oscillates, it produces oscillations in the electrical resistance of the MTJ, and this is caused by what we call the TMR effect, which is called the tunnel magnetoresistance resistance effect. So this TMR then can be used to detect the voltage signals with amplitudes as large as tens of millivolts. Okay. So some of the distinctive features of the SNOs that are very appealing for neuromorphic computing is, first off, the oscillation amplitudes that are created can be used as for memory due to their finite magnetization relaxation, and that just helps for the device to imitate how neurons are able to integrate with each other. The second feature is the fact that the frequency and amplitude of the voltage oscillations are highly nonlinear, which that nonlinearity is seen as a function of the current or applied field. So this just allows for direct implementation of nonlinear activation functions, which helps to define how the output of a node is based on the input or the set of inputs given into the reservoir. The next key feature here is that it has the ability to couple with other STNOs. And this is really important because we want to make sure that devices are able to synchronize with each other and emulate how the neurons and other collective neurons act in the brain, so that way they're able to share and process information accurately and give those desired results or advantages that we want to see in a neuromorphic computing system. And then the last distinctive feature is that it's highly tunable. So that means it allows the synchronization to other oscillators via magnetic interactions. So like in prior years, it was mainly through simulations that researchers were able to prove how well reservoir computing does work, or how well like magnetic elements can be used in reservoirs for neuromorphic computing. But recently, they were able to create hardware-based or experimental architectures that could help with that. And one of it is with this example on the left, and this is what they use for speech pattern recognition. So what happens there is that they're using a time multiplexing pre and post processing using a single STNO, as you can see in the middle. And this STNO is used as a reservoir to help to recognize and classify spoken digits. So in this image on the left, they were able to, it's just a particular example of how they were able to use the STNO to recognize a spoken digit of 1. And they've done this for several other numbers and recorded that. So what is happening here is that we have the input signals that are given into the oscillator by modulating the amplitude, as you can see in the input audio file. And this amplitude is modulated using DC driving current, which then creates a readout, which is the power output of the SDO. On the right image is another kind of pattern recognition that they were able to achieve with reservoir computing. And over here, it shows how you can couple several nano oscillators to help recognize vowel sounds or letters. So on the bottom image on the right, the way they were able to do this was they imputed 2 microwave signals into a strip line to the oscillator. So we see those 4 images at the bottom there, which is the parallel connection of the STNOs, and the frequencies are tuned by using the DC biasing current to adjust those frequencies. And without tuning of the with the currents, with the tuning of the current, they're able to create a synchronization pattern between the oscillators there to correspond to the desired output, which is the vowel sounds that you're looking for. So these are one application of that they've used STNOs or neuromorphic computing to show its viability. And this is with pattern recognition, but there's so much work being done out there with various other devices like domain walls or even schemions to help design devices that can be used for neuromorphic computing. That concludes my presentation. Thank you.